So hi everyone, and welcome to another installment of the U of A Geotechnical grad seminars. Today we're excited to have two gentlemen from Rocscience here to present about their company and the applications of their software. Before we dive into that, however, I'd just like to note that the U of A Canadian Geotechnical Society student chapter will be hosting a Quarantine and Learn event on Friday of this week. The event will be held from 5 to 6 p.m. where there will be two speakers talking about what it's like to work as a geotechnical and geoenvironmental engineer here in Canada. The event is more geared towards undergraduate students. However, I think some graduate students would also get value from learning about their experiences here in Canada. Plus, there will be 3 Skip the Dishes gift certificate draws for individuals who attend, so you could get a free meal out of the deal. I'll post a link in the chat box if individuals are interested in attending. Today, our presenter is Dr. Sina Javankhoshdel. He received his PhD from Queen's University in civil engineering and has been working with Rocscience since 2016. Dr. Javankhoshdel is a 3D geometry expert and modeler whose work at Rocscience has focused on developing Slide2 version 2018, where he helped add spatial variability analysis to the software. He's also well practiced in presenting, as he's an instructor for workshops, webinars, short courses, customized courses, and conference presentations. Before we jump into Dr. Javankhoshdell's presentation, however, Robert Bradford, a geotechnical sales engineer with Rocscience, will help provide us with a brief company overview. Join me in welcoming Sina and Robert.
All right. Thank you, Kevin. Good afternoon, everyone. So as Kevin mentioned, my name is Robert Bradford, and I am a geotechnical sales engineer here at Rocscience. And I'm just going to give a quick company overview before passing it off to Sina, who will talk a little bit more in depth about our programs. So jumping right into it. This is our head office located downtown Toronto. At the moment, we have a little bit more than 50 full-time employees. And more than half of our employees actually hold advanced degrees in engineering. Here you can see our head office located downtown Toronto. We're expanding at quite a pretty good rate at the moment. We also have an office in Lima, Peru, in Accra, Ghana, and on the east coast of Australia. And as you can see, we have resellers all over Asia, Europe, and in Brazil. So we currently have 16 programs. We typically categorize them into 3 subcategories: slope stability, excavation design, and geotechnical tools. And if we just go through those categories one by one, first, slope stability. So a good portion of our software programs fall under this category. Starting with Slide2. Slide2 is definitely our most popular program, not only in North America, but around the world. And for those of you who have used Slide2 in the past, you know it's not just a 2D limit, equilibrium, slope stability analysis program. It also has a full finite element seepage module. The 3D version of that is Slide3. We're gonna demo Slide2 and Slide3 a little bit later, so you'll get a better idea of what these programs look like. Slide3 is a 3D limit equilibrium slope stability analysis program. Next, we have a few software for slope stability of rock, starting with RocPlane. RocPlane is a planar wedge analysis for slopes, rock slopes. Next is SWedge for surface wedge analysis of rock slopes. RocTopple for toppling stability analysis of rock slopes. And last but not least, RocFall, which is a really fun statistical analysis program for rock falls. And we're hoping to have the 3D version of RocFall in a year or two. Next category is excavation design. And we'll start with RS2. RS2, we'll talk a little bit more about RS2 a little bit later as well. It's a 2D finite element analysis program. The 3D version of that is RS3, also obviously finite element analysis. Next is rock support. This is used for estimating deformation in circular excavations in weak rock. EX3 is our boundary element program. It's used for 3D stress analysis for underground excavations. And then there's Unwedge. Unwedge is an underground wedge stability analysis program. And then the last category, sort of a miscellaneous category, is called geotechnical tools. First, we have Settle3. Settle3 is a three-dimensional program for the analysis of vertical consolidation and settlement under foundations, embankments, and surface loads. RS-Pile. RS-Pile is a general pile analysis software program used for analyzing driven pile installations, laterally loaded piles, axially loaded piles, and as you can see in the middle there, it also does grouped pile analysis. RS Data. At the moment, it's still called Rock Data, but we will be having a release in the coming weeks. It'll officially be called RS Data for rock and soil data. This program is for the analysis of rock and soil strength data. C-Pillar. C-Pillar is used for evaluating the stability of surface or underground crown pillars. And last but not least, we have DIPS. And DIPS is used for the analysis of orientation-based geological data. So with that, I will hand it off to Sina to share his screen and talk a little bit more about slide 2, slide 3, RS2, and RS3. So,
okay, can you see my screen?
I can, yeah.
Okay, thanks, Robert. Hi, everyone. Thanks for having us here today. First, I'm gonna turn off my video. That you don't need to see my face while I'm presenting. Today, I'm gonna talk about some basics of slope stability analysis using Rocscience software. I'm going to talk about 4 major software packages that we have at Rocscience. Basically, we have a slide 2 and a slide 3 that they do a limit equilibrium method, and RS2 and RS3, as Robbie mentioned, they do 2D and 3D finite element analysis. So I'm going to start with limit equilibrium. I'll talk about some basics, and hopefully I can transfer some useful information to you guys today. Limit equilibrium method is one of the most common methods used for slope stability analysis and design. I don't want to say more than 90%, but definitely more than 80% of the engineers, they use limit equilibrium. Still, they use the limit equilibrium for the design purposes. So it's a very famous method, and I would like to start with this one. So if we start with the 2D limit equilibrium analysis, probably most of you are familiar with this picture, sort of pictures. We have some sort of grid search and circular slip surface with some slices. This is the method that's used by most computer programs, and you can model almost anything. You can define the different soil layers, groundwater condition, external loads, and etc. To calculate this number, which is the factor of safety to show the stability of the slope, there are different methods, some numerical methods and some methods like limit equilibrium, which is called method of slices as well. The reason that it's called method of slices is because first, in the limit equilibrium analysis, you have to assume a critical slip surface, and then we do different search to find the most critical slip surface. But you cannot find this number using just one surface and the information that this surface provides. So to make it simpler, you have to divide it into different segments called slices. And we solve these equations and find unknown parameters to calculate the factor of safety. I'll show you some of them. That's why it's called method of slices. When it goes to 3D, three-dimensional analysis, I don't know why it should. Method of a slice is going to be a method of columns. The same assumption is going to be used for the 3D slope stability analysis. So basically, if you look at this picture, this is the 2D version that you all know. We just add one more dimension normal to the plane of the model, and add more dimension to it, one more dimension to it, and it's going to be a column. So method of slices is going to be changed to method of columns. So the same concept, the same calculations, but it's in 3D. So there are some basic fundamental concepts in the limit equilibrium analysis. I need to see the chat. Some of these assumptions are basically, when we assume a theoretical slip surface, we assume that all points along this slip surface are on the verge of failure, which means that driving forces are equal to resisting forces. For example, driving forces can be the weight of the slip, the material above the slip surface, any live load, dead load that you have above your slope. And resisting forces can be like shear strengths of the material. And in general, if these driving forces are greater than the resisting forces, we mentioned that the slope space or factor of safety is less than 1. And if the driving forces are less than resisting forces, factor of safety is going to be greater than 1. So basically, the ratio of the resisting forces divided by the driving forces is going to be factor of safety. So this is the concept, but why we call it limit equilibrium? Because limit equilibrium means the perfect equilibrium between the forces driving failure and those resisting failure. To calculate factor of safety. So there are 2 steps to calculate factor of safety in the limit equilibrium analysis. Basically, you compute the shear strength required along the potential failure surface to maintain stability, and then compare the required shear strength to available shear strength. How can we calculate available shear strength? You're familiar with, for example, Moore-Coulomb equation, like this part of this equation. When you have cohesion, friction angle, parameters that you have, your soil properties have, you can calculate the required, the available shear strength. Or if you know these parameters and you want a factor of safety for design purposes, for example, for a slope stability, the design factor of safety is 1.5. And you want to calculate the required shear strength, you can use this formula. Remember this formula, I'm going to use it later in the presentation again to prove something. So for now, just keep this in mind. As I mentioned, limit equilibrium is method of slices. So let's say we have n slices. We have several shear and normal forces at the bottom of a slice or inter-slice forces. In general, we have 6n-2 unknown parameters. We have some equilibrium equations as well. Moment equilibrium, force equilibrium in x and y direction, and there are some assumptions as well. So basically, we have 4n total number of equations. So you can see that the number of unknowns that we have is more than the number of known parameters, known equations. That's why there are these many 11 different methods that we have actually in the Slide2 software that you can choose to calculate factor of safety. So what is the difference between these methods? It's just in the assumptions that they use to solve these equations, because you need to have some sort of assumption to be able to solve these unknown these equations and find unknown parameters. For example, Yambu and Bishop, Yambu assumes that both of them, they assume that there's no shear interslice forces. Yambu satisfies the force equilibrium, Bishop satisfies the moment equilibrium. Yambu always gives the lowest factor of safety as well. This is just a checkpoint. But the most rigorous methods are Spencer and Morgenson Price, that they satisfy all the equations. So These two are the methods that we recommend people to use together with Yambu, because Yambu is always the lowest, so you know the limit of the factor of safety. In 3D, we don't have those 11 methods in slide 2. We have only 4 methods that we recommend people to use. So this is what we have in the slide 3 software, 4 different methods. However, regardless of the methods of calculation of the factor of safety, there is something very important that you should know. Searching for the critical slip surface is the most important steps in the limit equilibrium analysis. If you ask a geotechnical engineer who has 30 years of experience, what is limit equilibrium? What you hear is limit equilibrium is a circular bishop method of analysis. It used to be like that, but it is not anymore. And limit equilibrium is an advanced method now. But for traditional purposes, we keep it in our software. We use circular search method as well. But what we have, you can see our database is much stronger for non-circular search methods, is this. And for the non-circular, we have 3 meta-heuristic search methods that actually they are global optimizations to calculate factor of safety. Called cuckoo search, simulated annealing, and particle swarm. Very weird names because we brought them from different fields, from chemistry, from other fields. But these are non-linear solvers using optimization. So basically, the factor of safety equation is non-linear, and these are non-linear solvers. So why not using them for the calculation of the factor of safety? The same in the 3D sphere is similar to circular, ellipsoidal is similar to non-circular. So we recommend definitely in 3D is different from 2D, because 2D sometimes you have circular slip surface, but in 3D you barely have circular and or spherical, and you should have ellipsoidal search mechanism. The grid search that I showed you for circular, for a sphere in 3D, it's gonna be like this, a cube search that you have. If I want to show you how these global optimizations works, this is a temperature diagram, and the goal in this diagram is to find the lowest temperature. As you can see, there are different points starting randomly at different locations, and their goal is to focus to find the lowest temperature. This is exactly similar to factor of safety calculation. We are looking at the lowest factor of safety, and we are using these types of optimization, global optimizations, to find the lowest factor of safety. On top of this, we have something unique at Rocscience, because some companies, they do have optimization, but at Rocscience, we wrote this code in-house. This is a local optimization called surface altering optimization, which means that after you found, let's say this green slip surface is the critical slip surface that you found using cuckoo search, for example, we applied one more step of the optimization to the most critical slip surface to find the lowest factor of safety. So we have one more level of optimization in our software as well, which is very helpful. I'll mention again later why this is helpful. But in general, you need to, at the beginning in the limit equilibrium or finite element analysis, you need to create your geometry first. 2D geometry is very simple. There are just a bunch of polylines that you draw and you create your geometry. You put a load here, maybe a water table, and the software is going to calculate factor of safety. However, in 3D, the story is a little bit different, because in 3D analysis, sometimes you create an actual geometry similar to this one. This is an open pit, and this is an actual model, actual field that you are creating. And there are different ways of doing it. The easiest way is if you have a 2D geometry, give it one more dimension, which is the extrusion depth, and it's going to be a 3D model. Very simple. But this is not 100% 3D because you just extruded a 2D model and it's symmetric. Unless you have a non-symmetric boundary condition. For example, if you have a load here or a different water table at different locations, that's going to change the story. Actually, this is the example that I'm going to show you today. I'm going to extrude the XF file, but with different boundary conditions. Another way is to draw a polyline and then make this polyline a surface or a volume, which is going to be used in the 3D analysis. Or if sometimes you have a tunnel, so you use a cylinder or a box for some other purposes. And when you have these types of geometries, you can use the built-in geometries that we define in the software, like a sphere, box, a cylinder. But in more than 80% of the cases, engineers, they have surfaces and volumes in different software packages. For example, AutoCAD or Civil 3D or LibFry. When you have surfaces and volumes in those software packages, you can directly import them to our software, Slide2 and RS3, the 3D software, and use them to create your actual geometry. But something that you have to keep in mind that most of these surfaces, 99% of them, they have issues because they are directly coming from the field, go to Autodesk, and then we want to bring them in our software. There are some missing information, some holes, some issues with the surface. And Slide2 and RS3 are one of the few software packages, commercial software packages, that they have something built in called repair tools that you can actually repair whatever you bring to the software. And you don't need to take it to a third-party software, repair it and bring it back to our software, which is very unique. In general, our geometry tools are very strong for 3D analysis. And also, as you know, you may have boreholes from your field to create your layering of your soil profile. And in most of our software packages, we have a tool called Borehole Manager that you can define the thickness for each material for different boreholes, and the software automatically creates your profile for you, which is very unique as well. So let's go to our first demo. This is a levee. Levee is an embankment. And we have a shear wall here as well, and a water table on the upstream. So I would like to model this in 3D and then show you the 2D and 3D results. Just limit equilibrium for now. We get to the finite element as well. So to do so, I open a Slide3 software. You can see we have 4 different regions because we have, if you say we have 3 dimensions, these are 3 dimensions, and this one is the full 3D. For this model, I would like to import a geometry that I exported from one of our 2D software packages. So let's say you have a DXF file, bunch of polylines, and you want to create that model that I showed you. So if I open this here, you can see that this is our 2D. When I bring it from a 2D software, I need to rotate it 90 degrees around the X axis. If I click on preview, you can see it properly. When I bring it in, you'll see it. So basically, the front of my model is going to be like this. So these are just a bunch of polylines that I want to use them to create a 3D model. Before that, I'll go to project setting. In project setting, you can set up the initial conditions that you want, the initial options. So I would like to choose Yambo and Spencer, as I mentioned. And for units, I would like to have empirical units. I hit OK. It's going to say, do you want the unit system to be changed? I said yes. And then now we are OK. So let's select all these lines. And I want to give them one more dimension, which is the extrusion that I mentioned before. I would like to have these polyline in the center of my model, so that I started extruding 100 meters before that point and extruded for 200 meters. In this case, you can see it here, my section is in the middle and it's a closed volume, and when I hit OK, this is the 3D geometry created. But there are several pieces. It is not 100% complete. To make different regions, you have to select the extent of your model. So you have to set external. External is the piece that the software does the calculations on top of this piece. So I set external. You can see there is a lock in front of that piece. It means that the software only works on the pieces that they have lock in front of them. Other pieces, they don't have the lock. So what we need to do is to use an option called divide all geometry to make these pieces part of our external. Basically, make our different layering. Let's see what happens. First of all, after using this option, everything has a lock, and you can see that now we have different pieces. We don't have just one big piece, which is good, which is what we are looking for. If we go to the material properties, I haven't defined anything here. There are different categories of different types of material properties, more Coulomb, anything that you want. We have a very strong library. But there is an option in the Slide 3 software that if you create a model in advance, Slide 2 or Slide 3, you can use the properties of those models. So I have this model in advance, and I just import the properties of that model. For example, this one. And the software is going to import. You can see these properties are defined in that model. And when I hit OK and I go to the define material again, these are the properties that I import, which is good. To assign each piece the property that it has, I normally use a 2D tool that make it simpler because it's a section, 2D section, and you can assign material properties. This one is symmetric. It's very easy. But if you have several pieces, a non-symmetric model, you can use this tool to apply different material properties. So in this model, we have a levy field. We have a retaining wall. You can see how easy it is to apply. Then we have a fat clay here, silty clay for this layer and here, and another fat clay here. So material properties are assigned. So this is my model, and if I use transparency, you can see that this is the 3D model. Very beautiful. So what I prepared in advance is a water table as well. So this is a water table. I prepared the surface. I could create it here, but to save some time, this is the water table. I just need to go to groundwater, add water surface. It's going to recognize this surface. And when I hit OK, it's going to apply the water table to all of my material properties. And then this is going to be my water table as well. You can see it here. The other thing is I'm going to use the default cuckoo search surface altering optimization that I was talking about. If you want to apply any filter to your model, you can do that as well. But I don't need to change anything here. Everything is set. You just need to save your model and compute. So let's save it somewhere and hit compute. So let's see what happens when we compute this model. I do it here because I want to show you how fast is our software. So basically, I'm using two methods. You can see Yambo is faster because it's a simpler approach. It has less equations, and you can see cuckoo search starts. And after cuckoo search, we have another optimization, which is the surface altering optimization. I'm running this on a laptop, so it takes about 1 minute and 20 seconds. You can see that now that it's applying surface altering, still the factor of safety is going down. It means that after the second optimization, it is still useful to do this optimization to reduce the factor of safety. So this is doing the optimization now. It will be done in a few seconds. If you want to increase the speed of the computation, because all of our software packages, they're parallel. It means that they use all the capacity of your CPU. Still, I can do other stuff using this computer. You can change the execution priority as well. So it's up to you. I keep the normal, and you can see that the Yambu is done. It is waiting for Spencer to be finished. So after this one is done, we'll discuss the result and then a little bit of 2D limit equilibrium. Please feel free to type down your questions if you have any in the Q&A section. Okay, this one is done as well. It's saving the results. Okay, so let's go to the results. Factor of safety of Yambu is 2.021 and Spencer is 2.16. So you can, as I mentioned, Yambu gives the lowest factor of safety compared to the other one. And this is your critical slip surface. There are several tools to look at the results. If you want to look at all the surfaces, you can just click on show all surfaces. And these are all the surfaces that Cuckoo searched to find the critical slip surface. As I mentioned, this is method of columns. So if you click on this column viewer, you can click on any of these columns to see every property that they have, all forces and all the properties. And we have a material info. You can see the slip surface goes through two materials. So by clicking on each of these, you can see which material is in it. So this is very useful information as well. You can always export the information to Excel as well. The other feature that we have here is the contours. So you can look at the contours of your critical slip surface as well. So this is our critical slip surface. These are different contours. For example, if you want to look at the base cohesion, you can look at these two. It means that one part of it has the cohesion of 50 and the other one is 30. So you know that it's going through two different materials. Another very important feature that we have is called surface safety map. It shows you that what part of your model is safe and what part is not. You can see around your levee, you have all red. And it means that this region is the most critical region, which is a very useful information when you do slope stability analysis. Now we are interested to see what happens to the two-dimensional results, 2D results. We have built-in a Slide2 engine in a Slide3 software that you can create a 2D section code and use that engine to do the analysis. So if I create this section, you can see that this section is created. And then selecting this section, you can see that the Slide2 compute. By clicking on this option, you'll see that the engine of the Slide2 is going to start running. Something that I have to specify, sorry, in advance, is the right to left or left to right in 2D. Let's try it again. So this is the Slide2 compute. It's very fast. And when we are in the result tab, it shows a line which is the 2D results. You can see 2D results compared to the 3D results, a Spencer factor of safety of 2.1. In general, 3D results are larger than 2D, but when you have an extruded model like this with no unsymmetric boundary condition, you should get very close results, similar to here, and close slip surfaces. If you are interested in seeing your 2D model, you can just open the Slide2 modeler, selecting this section, and this is your 2D model. And you can see the 2D results here as well. So yeah, Boeing 1.96, Spencer 2.1, and similar to the 3D, you can look at all the slip surfaces. This is cuckoo search. You can see this is not just a grid region here. It searches everywhere. You can look at the slices and also slice information, same as the 3D one that I showed you. And this is similar to the contour of the slip surface. And let's look at that base cohesion. You can see that we have cohesion of 50 here, 30 here, exactly the same as the 3D that I showed you. Okay, let's move on. So we showed you the results of 3D analysis, factor of safety of 2.16, and the 2D results on top of the 3D results. They are very similar. Okay, now let's talk about finite element analysis. We have RS2 and RS3 as our finite element analysis, 2D and 3D. They have more applications just rather than just a slope stability analysis. So in general, finite element analysis means that we build a complicated object from simple interconnected blocks and elements. For example, if you want to model this airplane using finite element analysis, you can divide it into different blocks, which we call it mesh, and look at the stresses at different locations. Basic idea is, let's say you want to find the area of this circle, you divide it into different triangles, and if your triangles are small enough to cover the whole area, they go to infinity basically, you can find the area of the circle using these triangles, which is the concept of, very similar concept of the finite element analysis. In general, in finite element analysis, we divide our domain into small interconnected elements. Every element has its own function, which we call it in finite element displacement function. Every element is linked to other elements. They don't change. They don't get disconnected after deformation. And based on stress-strain properties of the material, behavior of the system of nodes can be determined. So we need the displacement function, and we need the behavior of the system, finding the behavior of the system using the stress-strain properties of the material. In general, every step is the same as limit equilibrium, except you may have some additional boundary conditions like these restraints and also mesh. Other than that, everything else should be similar. This is 2D and this is 3D. And the 3D mesh in our software is very strong, actually. And if you have a critical region, it's going to refine the mesh for you automatically. For the slope stability analysis, using finite element, we use a method called shear strength reduction method to compare the results with the limit equilibrium analysis. This is from Bishop. This is the formula that I told you to remember. Actually, this formula is the basic concept of shear strength reduction method. So if you look at this equation, this is the one that I showed you before. So what happens here is, let's say you have the more Coulomb shear envelope. You use a factor, a number, to reduce this shear envelope. To do this, you need to reduce C and phi, or soil parameters. So reducing C and phi is going to cause the reduction of the more Coulomb shear envelope. This is the basic concept of SSR. It's an iterative process. So we reduce the strength of soil material by a factor. We call it a strength reduction factor, or SRF. Compute FEM model. If analysis fails and does not converge to a solution, we reduce this SRF, initial SRF. If it converges, we increase the SRF. And factor of safety is this SRF actually when the value that initiates the failure. So it is factor of safety, and it is possible to compare it to limit equilibrium. So you've got something here. If we have the same conditions in the limit equilibrium model and finite element model, they should give the same answer, the same factor of safety. This is some concept that a lot of people they misunderstood. They think that finite element analysis always gives a better solution. It is wrong. I'll show you an example today that it's wrong. So they should give the same answer unless you have some complications like joint pattern in the finite element that limit equilibrium itself cannot handle it. So in that case, sure, finite element gives better answer. The last part of the presentation that I wanted to show you is how to model water in limit equilibrium or finite element, actually. There are different ways of doing that. Some software companies, they have some additional software just to do the water analysis. It's not like that in our software. We just have it as an add-on. So we have different options. You can either use water surface similar to what I did for my model. You can use the pore water pressure point set. But if you want to do it very accurately and correctly, you should do it numerically using a finite element seepage analysis, which has two options of steady state and time-dependent transient. This finite element engine, we have it in Slide2 and RS3, so it's an additional engine. So basically, in RS2 and RS3, we have two finite element engines. And in Slide2, we have one limit equilibrium and one finite element engine. There are some basic concepts. What is pore water pressure calculation? How we calculate pore water pressure when we only have water table? We define the total head as the top of the water table to the datum. This is the total. Elevation head, this is the point A below at the last point of your water. Elevation head is from A to the datum. And total head minus elevation head is going to give you the pressure head. Pressure head times unit weight of the water is going to give you the pore water pressure. This is what we did in our example that I showed you. But for finite element numerical analysis, pore water pressure analysis, you need to define some sort of boundary conditions. What are these boundary conditions? For example, let's say you have these. You have total head, zero pressure, nodal flow. For example, in this picture, the head at A, B, C, and E, F, G, they are constant. So this is constant head or total head. We put a total head as the elevation of the water here. We have no flow, which is this boundary, the rock boundary. And we have seepage face. I'll explain about seepage face later. About total head or constant head, let's say you have a river here. When it's constant, it's always there, so your head is constant. It's not changing. Even if you have dewatering, still you have this river here, it's still not changing, your head is constant. But when you dewater and there is no water here, you don't have the total head, constant head. A nodal flow, when you pump the water from a specific point or dewater from a specific point, it's going to be a nodal flow. Seepage face is defined as the point that always your total head is less than your elevation head. So this big arrow should be smaller than this. In other words, your pressure head is negative. So what does that mean? It means that there are some regions like here and here. When the water reaches this air, it cannot go out. There is no water above this point, because if there is a water above this point, your pressure head is not going to be negative. So this is very important because you have to define it in your model. But how do we know that? You just guess a region that it's going to be seepage face. There shouldn't be any water above it. And the software is going to calculate it automatically. So you just define it and for a specific region, and the software is going to be calculating it for you. And infiltration, when you have rainfall or evaporation, you can define the infiltration. So let's go back to the demo. This is a little bit different demo. We use the same geometry. Slide3 and RS3, they share the same geometry. So I created the model in a Slide3. Now I can take it to a RS3. The same in slide 2 and RS2. RS2, you can drag and drop slide 2 models into RS2 models and do the analysis. So we have integration between our software packages. For this one, let me tell you the story behind it. We have this levee model. We have a total head of 115 feet here. But when we have this head, there is a pore water pressure in this region, which causes the pore water pressure is always bad. It reduces the factor of safety. It reduces the effective stress. So sometimes to reduce the pore water pressure, they use something called relief valves. So this relief valve has a total head of 106, which is less than this 115, which means that we are reducing the head at this point. So if we model it in 2D, this one is RS2 software. We did the seepage analysis here. When you do the seepage analysis, you can see that the pore water pressure here, the region is red. This is without relief valves. But when we define the relief valves to reduce the pressure, you can see that this region is blue, which means that we are reducing the pore pressure at that point. Then when we did the slope stability analysis after that, for the one that there is no relief valve, factor of safety, the green one is from RS2, is 1.19. And from slide 2 that I told you, they should give the same answer, RS2 and slide limited equilibrium of finite element, is 1.18, and the same region. For the model with relief valves that we reduce the pore water pressure, factor of safety goes up to 1.65 in finite element and 1.63 in limited equilibrium analysis. So you can see how different is going to be the factor of safety. There is one point here, and then I'll go to my model. In 2D, when you define the relief valves, because in 2D modeling, you assume that the normal to this plane is infinity. It's a plane strain condition. So we assume that these relief valves are infinity, and they're all along your model, which is not 100% true. But you cannot model it in 2D because you cannot specify the distance in 2D. But when you model it in 3D, you can put these relief valves at different specific distances. This is what I'm going to do for this model. So what I'm going to do, I'm going to create an RS3 model. I'll do the seepage analysis in the RS3 model, which won't take long. And we're going to have probably 5 minutes for questions. And then I'll compare the final results. So as I mentioned, you can import slide projects into RS3, slide 3, because they share the same geometry. So the geometry that I created in slide 3, I don't need any mesh or restraints for now. Sorry, it's going to come here. So this is the model that I had in slide 3. Now I brought it to RS3. For the seepage analysis, you don't need any water table, so I'm going to remove the water table. As I mentioned, the elevation of the water on the upstream is at the elevation of 115 feet. So I'm going to add a plane at the elevation of 115. I want to use this plane to cut my model. So I use the divide all option that I mentioned because I want to apply the boundary conditions at that level. So I need to cut my model at that level. The plane disappears, but it cut my model at this level that I wanted. So the other thing that I need to do is to go to the groundwater and change it to a steady state. And I want to check the negative pore water pressure. This is for unsaturated condition. I don't want to have any positive pore water pressure, negative pore water pressure. Then we go to the groundwater tab. Let's define some boundary conditions. We need a total head of 115 on the upstream. And also I told you have to define the seepage face somewhere in your model that I'll show you there, and hit OK. So let's add these boundary conditions. We should select the face. So this is the upstream of my model where we have total head, and this is where I cut my model. I wanted to have this face as well, and I'm going to apply the total head of 115 on that side. And we go to downstream. I don't want to have any water above this region, so I have to define it as a seepage face. Now, what I want to do, I would like to have my relief wells, instead of infinity, I want them to be 50 meters apart. So to do that, I'm going to hide all these guys, and also I'm going to hide these two pieces because my relief wells are defined here. So I select the top face of this guy and go to add weak drain. So I need to draw a region around the relief well location. So click done. So this is the weak drain or relief well dialog. I'm going to change it to relief well. The pressure is going to be 106.5. The diameter is going to be 0.3. X is going to be 100. I want them to be 50 feet apart, and minus 77.632 y0, and the height is going to be 12.8. So this is the definition of my relief well. And when I hit OK, you can see these blue lines. These are my relief wells, 50 feet apart. So I'll bring everything back. The next step, you don't need restraints when you do the seepage analysis. For the seepage analysis, you just need mesh. So I'll go to the mesh tab and I'll define the mesh. I'll change it to 4-noded, graded, and I'll mesh it. This is the default mesh for the software. So it's done. This is mesh. You can see some place they're finer and some place they are coarser. You can see we have two engines here. One is the water engine and one is the slope stability engine. So I just want to do the seepage analysis. So I just click on the water engine, save it somewhere, and hit OK. So the seepage analysis, finite element seepage analysis, it's a very fast procedure. Now the model is saving. After that, this is a dialog. In the finite element, if this number is less than the tolerance, it converges. It's done. And we go to the results. Let me show you the total head that I defined. This is the total head that I defined, 115, and clearly this blue region is my relief well. So let's make a section cut in this model. I'm going to hide exterior contour, and I'm going to define two different contours, 2D contour planes, to show you how to define how the results are for the location that we have the reliever. So this is another contour. So if we look at this, you can see that there are different regions. If I show you the pore water pressure, it's going to be even better. You can see that these blue regions are the regions that I defined the relief wells for. And I reduce the pore water pressure. So this is the seepage analysis. If I want to do a slope stability analysis, I have to turn this on and then run the solid engine. I did that in advance. I just want to show you the results of the slope stability analysis. You can see that the factor of safety, this is the same model. If I want to show you the factor of safety and critical slip surface, factor of safety is 1.54. And the critical slip surface is gonna be here. You can see this is the region of the critical slip surface. I had this model in a slide 3 as well. So this is the result of a slide 3 factor of safety of 1.55. And if we look at the safety map, the same safety map region. I did it in RS2 as well. And this is the RS2 results. I just want to show you how these methods, they give the same answer. So for RS2 results, this is 165. And for slide 2 results, it's here. For slide 2 results as well, it's using Spencer method 1.63, the same as RS2. On the RS2 model, the red line is for the critical slip surface. So let's wrap up the presentation. So this is the one that I showed you, factor of safety of 1.54 in RS3. We have the maximum shear strain as well, if you want to look at them. And this table is interesting. When there is no relief well, factor of safety is 1.2 in both of the RS3 and slide 3 models. If they are 200 feet apart, factor of safety is a little bit larger. If we reduce the distance between the relief wells, factor of safety goes up. So you can play with the distance to have different factor of safety. And the last one is the 2D one, which there is no distance between, and it's assuming that it is infinity, normal to the plane, and factor of safety is 1.65. So this is an interesting output of the answers. Thank you, guys. I would be happy to answer any question.
Thank you, Dr. Sina, for your great presentation and the demonstration of the software. I think we're now running late for the seminar. I will just open the floor for 1 or 2 questions. Actually, we have a question from Fisha here. She was a Slide 3 user, and she's got a warning when she was importing 3D DXF file into the program, and she was wondering, like,
yes, I did see that warning. Yes, the reason for that error is there are some when you have the AutoCAD file, there is an option called create mesh or something. Probably the DXF file that you brought in or from Civil 3D, it includes some entities that they are always either void or they have some issues. So you have to take this to AutoCAD, fix those issues, and then import to a Slide 3 file. That's the issue.
Thank you. Another one is from Abel, and he was wondering, does Slide 3 allow the handling of discontinuity?
Yes, it can. Let me put it this way, not similar to what Finite element does, but we have 2 options. One is weak layer, that you define the weak layers as like similar to joints. The other thing is you can define some materials, like we have an option called generalized anisotropic, that you can define joints and joints orientations in your model. So you can define the base rock and also joints, and the software is going to find, actually that's very interesting, because this optimization that I mentioned, they're going to capture the orientations of the joints. Yes, so the answer is yes.
All right, thank you, Dr. Sina, again for your presentation and answering for those questions. I think that's end of this seminar, and I will encourage anyone who still have questions to send an email to Robert, and he posted the email in the chat already.
I would be happy to answer those.
Thank you. So with that, I would like to conclude this seminar, and thank you everyone for attending this. And I'm looking forward to see all you guys in the next one. Thank you.
Thanks.
Thanks, everyone.